So hello my friend, my name is Andika D, and today I would like to present to you about discrete distribution. And the first one theme that I want to present is about geometric and hypergeometric distribution. So what is the definition of geometric distribution? Basically, it's distribution of number of trials needed to get the first success in repeated Bernoulli trials. When to use this geometric distribution? So the first case is when the phenomenon being modeled is a sequence of independent trials, and there are two possible outcomes, which is success and failure. The last one is the probability of success, or P, is the same for every trial. What is the geometrical distribution used for? In such a sequence of trials, geometric distribution is useful to model the number of failures before the first success. The first distribution probability, there are 0 failures before the first success, 1 failure before the first success, 2 failures before the first success, and so on. Let's jump in straight into the real cases of those. So in large population of baccalaureate, or let's just say in the postgraduate, or someone who just graduated from the college, 30% of them have received and training and kartu prakerja. If some out of those population are randomly selected, what is the probability that the 6% sample is the first that has received training and kartu prakerja? So to deal with that, I'll reserve you some calculation of here. We can see that there is a p here. P, or the probability, is 0.3, which represent from here 30%, and we just passing this formula given x equals to 6 because there is a 6% sample, 1 minus 0.3 of the probability, and x to the raised power of 5 got from x minus 1, or 6 minus 1 equals to 5, times the p, or the probability, which is 0.3, and we got the result is 0.0504, or it's around 5% of the probability. That's all. And before jumping in the next one, we have to see that the distribution is always like this. When the first one, we find that this is the most likely value, and it keeps decreasing after that. That's the most unique from the geometrical distribution. And the next one, I would like to explain to you about the hypergeometric. In hypergeometric, we can address situation when the independence assumption isn't met. And just like before, there is success and failure categories. Hypergeometric distribution is often said to assume no replacement. We can see that this is the formula of the hypergeometric distribution. Let's jump straight in the real example. So see, if you are working in a factory and you have to handle the QC, you are responsible to counting on a 100 light bulbs and inspecting it. So a lot that contains of 100 light bulbs is inspected using the following procedure. 5 bulbs are chosen at random and tested. If all of those 5 lights up, the entire lot is accepted. Suppose the lot contains 20 defective bulbs. What is the probability that the lot is accepted? So we define the problem first. The lot is accepted if we choose 5 good bulbs from this 80. 80 comes from this 100. And we know that suppose we already know that there are 20 defective bulbs, and the remaining of this is 80 that work, and choose 0 bulb from the remaining 20 that don't work. X is the random variable equal to the number of defective lights, and from those we just pass into this formula. We got some calculation of here, and we find that the result is around 0.31 and 93, and that's around 32% if we're following this procedure. So next one, we jump to the multinomial distribution. What is this? Well, multinomial distribution is the multinomial probability when the outcomes come from a multinomial experiment. So the keyword is the multinomial experiment. What does it do? So it means that experiment, for example here in real cases, we can see an experiment of the blood. You can understand that the blood is separated into 4, isn't it? O, A, B, and AB. And in a random sample of 10 Indonesian, what is the probability of the 6 have blood type of O, 2 have type of A, 1 has type of B, and 1 has type of AB? We're passing the formula here, and we got the 6, x1 equals to 6 comes from the 6 blood of O, 2, x2, and this is 1 type of B, passing x3, and 1 has type of AB, passing x4. And we just do some calculation here, and we got the result of 0.21 and 90, or around 22% of it. So that's all of the multinomial distribution. Let's jump straight to the most interesting part here, which is chi-square distribution, which is part of the continuous distribution. So what is chi-square distribution? Why we use it? So let's say that Naruto comes to the Konoha camping and he wants to just think about the proportion of campers there, and he asks his friend Sasuke. Sasuke said that maybe out of 100 campers in Konoha, there are 50 men and 50 women. And to not be exaggerating, he proposed and convinced Naruto that he takes 20 samples out of it. From those 20, the result is 11 of women and 9 of men. And Naruto said that, maybe yes, because it represents those 50-50. But what about his sample? 12 and 8. Maybe it's still yes, isn't it? What about how change to 13 and 7? It's kind of bad, difficult, right? Starting to be difficult, so yeah. Maybe we can say it's maybe to represent this number. But what about this number, 14 and 6? It still represent 50-50? Most probably no. But does 40 and 6 maybe still yes for Sakura? But then Hinata said, no, it's not. But Kakashi said, why not? It can be, yeah. So how do we deal with this problem? That's where chi-square test comes into play. What does it show us? Well, it basically shows data collected and data predicted. To understand first, we have to understand the null hypothesis concept. Null hypothesis is the claim that leads into the prediction. For example, there are 50-50 of the claim, which should be a 10 and 10, which results in 20 of the prediction, so it must be separated equally. So what if the problem we got the 13 women and 7 men? How do we deal with this problem? How do we calculate and interpret using chi-squared? At the first one, we have to see at the formula of the chi-square, which is represented by the x square, and it be a sigma of observed and expected square divided by the expected value, which is followed to determine the sample size, determine the expected value, perform necessary calculation, and sum of the final column. Wait. It's too complex. Let's just jump straight into the table to see what does it mean. We got from this table sum of chi-square equals to 1.8. What does it mean? Well, it means that we have to see from the chi-square table first. There are a TF here. What is TF anyway? Well, let's see in that there are 3 persons, Naruto, Kakashi, and Sasuke. And the pairs, let's see, Naruto got Hinata here, and Sasuke got Sakura here. But what about Kakashi? Kakashi will left with no choice, isn't it? So from there, Kakashi have to leave and choose with Lee, where from this simple explanation, we can see that the degree of freedom is always n minus 1. So what about here? We got degree of freedom is 1, isn't it? Because man and woman is 2, 2 minus 1 is 1, isn't it? So we have to focus on the df equals to 1. So from here, we focus on the 0.05. It's agreement by scientists that 0.05 is the pivot point and most important point. So everything that is less than or equal to 0.05 will define as not reject the null hypothesis. So what if we got a number of 16 and 4, which result to 0.2? I mean 7.2. Well, 7.2 is far greater than 3.841, isn't it? So we can see that it's being right placed here on the green color. So it means that it rejects null hypothesis. So to make some conclusion of those all, if chi-square value is less than or equal to value of 0.05 probability, we cannot reject the null hypothesis. While if it is chi-square more than value of 0.05 probability, we can reject the null hypothesis. That's all that can I explain. Thank you, and I hope you understand.